I have discussed several aspects of free vibration, forced vibration and their equation, their solution, and now I will try to take a few problems as an application actually, so that it will be helpful to you. So, few problems I will take in this module and try to show you how to solve them, different aspect to find out different parameters. And you can see here, let me see the first problem, and you can see an unknown weight W is attached to the end of an unknown spring K. That means both mass and spring is unknown, and the natural frequency of the system was found to be 90 CPM cycle per minute. If 1 kg weight is added to W, the natural frequency reduced to 75 cycle per minute. Determine the unknown weight W and the spring constant K. So, this is the problem, and actually main thing what actually to be used in this, we know that this is actually given frequency of the system cycle per second f equal to given 90 cycle per minute, or it will be 90 divided by 60, it will be 1.5 CPS cycle per second. That is the unit has to be used, and you know omega equal to twice pi times f. So, this will be equal to 2 multiplied by pi multiplied by 1.5, that will be omega, and we know that your omega equal to under root k over m. Okay. Under root, this is the only thing you used here, and if I do that, and then you can see that you will be, if you do this, then omega square will be equal to under root k over W multiplied by G suppose, and so that will be equal to, if I square this one, it comes 88.92. And another case, actually when actually f equal to 75 cycle per second, then that will be CPM, that will be equal to 1.25 RPM, no 1.25 CPS, and then omega will be equal to 2 pi multiplied by 1.25. So, that means I can do another kg divided by 1 plus 1, that will be equal to your this square. So, that will be equal to 61.88. So, these two equation we have got, you can see. So, this is one equation 1 and this is equation 2, and you can see we can find out that equating these two equation, we can get equating equation 1 and 2. I can see, I can equate, I can find out k from here, I can find out k from here, and this I will equate, and then I will get actually 88.92 minus equal to 8.9 W equal to 61.88 W plus 61.88. I will get equating this, simplifying this using this two equation. From here I will get W equal to 61.88 divided by 27.23, that will give you 2.27 kg. And if I put this W equal to 2.27 kg, then I will get K equal to 201 kg per meter. So, this is the simple problem actually in the vibration, any vibration problem, the natural frequency is defined as omega equal to under root k by m, but here actually your natural frequency given in cycle per minute, and that to be converted into cycle per second, and from there actually this omega actually is nothing in radian per second. So, I have to convert f to omega, and what is the relationship between omega and f? Omega equal to 2 pi f, and that I will do, and from the given condition 1 I will get this is the equation, and from the given condition 2 I will get this is the equation. From these two, using these two equation, I can set this equation. From there I will get W equal to this, K equal to this. Simple thing we have done. That means I have not done anything other than under root K by M, or natural frequency equal to under root K by M. And simultaneously you have to keep in mind that natural frequency under root K by M is expressed in radian per second. That has to be remembered, and when it is expressed either in cycle per minute or revolution per minute CPM, or it can be also RPM, that means that has to be expressed first cycle per second, and if it is expressed in cycle per second, then what is the relationship between omega and f? F actually in cycle per second and omega in radian per second. So, then what is their relationship? Omega equal to 2 pi f. So, that to be used in addition to this to be used, and then condition 1 this is the equation, condition 2 this is the equation, then solving this I can get the both two unknowns. I have got two equations, so I will get that. Okay. So, let me go to the next problem, and you can see a spring and dashpot are attached to a body, and body weighing 140 Newton, and the spring constant is 3 kilonewton per meter. The dashpot has a resistance of 0.75 Newton at velocity of 0.06 meter per second. Determine the following for free vibration. Okay. So, free vibration actually you can see two things are given here. Your W is given, your W equal to weight actually given 140 Newton, and your spring K is given 3 kilonewton per meter. So, now you can see, and I know that damping force is given 0.74, that means damping value is not given. Instead of that, it is given damping force. So, damping force actually C times velocity or C times velocity equal to damping force. So, velocity is given 0.06. So, what is the value of C? Actually, C will be equal to 0.75 Newton divided by 0.06. Okay. So, that become this is actually it was in Newton, and this is actually meter per second. So, this will be 0.75 by that will be 12.5. Okay. C become 12.5, and I have to inspect whether the system is over damped, under damped, or critically damped. So, you actually see that when it is C over 2 m greater than under root K over m, then that is actually over damped, that already I have done, and C over 2 m equal to under root K over m, then that is called critically damped, and C over 2 m less than under root K by m, that is under damped. So, we can find out this value C over 2 m, C is 12.5 and 2 C over 2 I is W is 140 multiplied by 9.81. So, this was W. So, I have actually C over 2 m. Okay. So, 2 W actually here C over 2 W. So, W I can divide by G, then only so G will go here. That value comes actually 0.437 and under root k by m, it comes actually it is under root 3 multiplied by 1000 multiplied by 10 divided by 140. So, 3 kilonewton per meter. So, 3000 Newton per meter multiplied by 10 because of this. So, if I do this, we can say 3 multiplied by 3 kilonewton per meter. I think that is wrong anyway. That means 3000 multiplied by 10 divided by 140 and under root 3000 multiplied by 10 divided by 140 equal to 214 that is actually 214.3 21.4.3 under root 214.3, that become 14.6. So, that become 14.6. So, it is actually much bigger. This is much bigger than this one. You can see under, that means this is under root k by m become much bigger. This becomes C over 2 m. So, this is actually, that means it is under damped. So, this system is under damped. So, this is the problem. That is simple thing what we have done. We have tried to explain that what is the relationship between damping coefficient and damping force. Actually, velocity multiplied by the damping coefficient is the damping force. From there I have got the damping, and then we know that different relationships C over 2 m greater than under root k by m, then over damped, C by 2 m under root k equal, then critically damped, and C over 2 m less than under root k m, then under damped. So, then I have computed C by 2 m and then under root k by m, then we can see that this system is under damped. What is the meaning of it? Under damped means most of the system is under damped. Actually, it will be that oscillation will be there. Next, go to the third problem. Okay, this is the problem. Actually, you can see a counter rotating eccentric mass exciter is used to produce forced oscillation of spring supported mass by varying the actually counter rotating means actually it is like this, as I have explained before also. If the mass is like that and it is rotating like that, then because of that, when the mass is here, both are going downward. When the mass is here, then they are facing each other. So, no vibration. When it is here, it is going downward. When the mass is here, it is going here, it is going to get cancelled. So, that means it is producing a vibration like this. So, that it is nothing but rotating mass system. Okay, and of the and amplitude was resonant amplitude was 5 millimeter. When the speed of rotation was increased considerably beyond the resonant frequency, the amplitude approached to appeared to approach a constant value of 0.6 millimeter. Determine the damping factor of the system. So, this is interesting. Whatever observation I have mentioned there, actually I will show once again that one and then I explain. You can see here rotating mass system. This is the expression. Okay, the expression is what? The amplitude here, resonant amplitude, damping is unknown. Resonant amplitude U max actually 5 millimeter is given, and your U max actually 5 millimeter is given, and your and u max actually what for this type of u max actually by m e over m will be equal to under root 2 d under root 1 minus d square. This is the actually your expression for maximum amplitude, and this can be written also when the damping is not very large. This can also written as under root 2 d. Okay. So, I have got this, and that means that is 5, one equation is 5 divided by m e into e over m equal to under root 2 d. That is one equation I am getting. Okay. And another expression, another thing is mentioned that when the frequency is increasing considerably large, so towards here suppose, and it is approaching to a constant value amplitude, and that is equal to actually your 0.6. Here actually amplitude was when the amplitude omega is large, then your amplitude u become 0.6. So, that means I can say 0.6 divided by m e into e over m, and when the amplitude is very large, actually when amplitude is large, I can say u over m e into m, that is actually the ratio become, if I take this thing this side and this magnification factor becoming 1. So, I can write this as 1. So, that means from this equation I can write this as 1. So, that means this is equation number 2. So, from here what I can get, I supposed to know the machine detail, that means what is the eccentric mass, what is the eccentricity, what is the mass of vibration, nothing else known, only 2 information is given. From there I can solve this problem. How I just show you here, that if I consider this as the entire thing as one thing, then I can see from this equation I can get m e into e over m will be equal to 0.6. That means, this quantity now from this observation, this quantity together I get 0.6. Now, this 0.6 I have put here, that means I have another equation I have got, that is actually 5 over m e into e over m equal to 1 by 2 d. This is another equation I have got. This if I put equal to 0.6, then it is becoming 2 d will be equal to 5 by 0.6. 2 d equal to 0.6 divided by 5, or d equal to 0.3 divided by 5, and that means your d become 0.3 divided by 5. If I calculate, that become 0.06, that means 6%. Is it clear this problem? This problem what I have done, u max over m e e, I know that for resonance condition this is the expression, and if the damping is low, the under root 1 minus 1 d square is also close to 1. So, I can simply write equal to this. So, that means 5 divided by m e e by m equal to 2 d, this is equation 1, and another equation what actually when the amplitude frequency is very large, that time your magnification factor become 1. So, here actually magnification factor is u over m e over m equal to 1, that is another expression I have written. U is 0.6 as large frequency, and then m e over m equal to 1, that is another expression. So, from this expression I get m e e over m equal to 0.6. Now, if I put this one in this, that will here actually 5 by 0.6 equal 1 by 2 d. Okay. That means 5 by 0.6 equal to 1 over 2 d. So, this equation if you solve, then you will get d equal to 0.06 or equal to 6%. So, that means this I do not know any machine details, what is the eccentric mass, what is the speed, and what is the total vibration vibrating mass, nothing else is known, but by rotating the by increasing the frequency we have observed the resonance. At that point what is the amplitude is noted, and increasing the frequency is significantly large, and at that point when the amplitude becoming constant, that point what is the amplitude is noted. So, this actually one is 5 millimeter, another is 0.6 millimeter, and 5 millimeter is nothing but u max, and u max expression is this. From there I get equation this, and u actually general expression of magnification factor u over mu over m equal to this one, and for large frequency this quantity become 1. So, I have put this one, this is expression 2, and from here I get this equal to 0.6. This one if I substitute to this equation, then I will get 5 by 0.6 equal 1 by 2 d. From there d equal to 0.06, actually that is nothing but 6%. That means damping in this system is 6% only. Okay, this is another problem. Let me go to the next one. This is another problem actually similar. A single degree of system is excited by a sinusoidal force, and resonance at resonance the amplitude of displacement was measured to be 2 millimeter. That means u max, again u max equal to 2 millimeter, and at an exciting frequency of 110, that means very small. That means your response is something like that. Resonance is here, and at 1/10 frequency, that means u at very smaller frequency ratio, it is 0.2. And if you see that response, I have shown before, and I will show in the next slide, that when the frequency is less, your all response something like this. All at low frequency the amplitude is almost constant. So, this is the observation we can use. By using this problem can be solved. The displacement amplitude was 0.2. So, now nothing else is there. What is the magnitude of constant force, what is the vibrating mass, nothing is given, but what is the stiffness, but estimate the damping with similar way. The problem we have done previously, here actually reverse observation. Let us see in the next slide. You can see here that when it is a constant force system, this is the expression, that way u over f naught by k equal to under root this quantity, and you can see that when the frequency is very low, this become 1. Okay. That is observation, and u max actually, and another is u max over f naught by k equal to 1 over 2 d under root 1 minus d square, and nothing but 1 by 2 d. This is one observation, this is another observation. Using these two observations, if I use this observation, what I will get, u is actually 0.2 equal to f naught over k equal to 1, or f naught over k equal to 0.2. And from here actually what I am getting, this is this amplitude was um was 2 millimeter, this was 2 divided by f naught over k 0.2 equal to 1 by 2 d, and from here I can get 4 d equal to 0.2, or d equal to 0.2 divided by 4. So, equal to 0.05, or you can say it is 5%. Okay. So, this is one of, that means at frequency ratio, very less frequency ratio, when the frequency is very less, then this entire quantity become 1, magnification factor, this magnification factor become 1. So, this is u and this is f naught by, so this is 1. From here I get 1 f naught over k equal to 0.2, and u max by f naught over k equal to 1 by 2 d under root 1 minus 2, that is also equal to 1 by 2 d. So, this is 2, and this I am getting 0.2, and this is nothing 1 by 2 d. solving this I can get damping equal to 5%. Okay. So, otherwise some people can also try to solve this problem by how they can solve it. Actually, one is actually you are getting 2 divided by f naught over k because divided by 1 over under root 1 plus omega over omega and actually 1/10. So, 0.1 square whole square plus 2 d multiplied by 0.1 whole square. One can set this is one equation, and another equation one can do no, this is 0.2. Another equation is 2 over f naught over k equal to under root 2 d. So, solving these two equation one can also find out, but if I use that at lesser frequency, the frequency ratio amplitude actually is a magnification factor, this quantity become 1, that is that means if I use this as entire thing as 1, then it is easy to solve quickly, and in fact if I use this expression and this expression solve, finally instead of 5% we may get a 4.999% or something, or 5.111% or 5.01% or something like. So, very close value will get. So, better to use this observation, that means at very less frequency ratio your magnification factor is 1 and resonant frequency magnification factor by this equation, and then equating these two one can get the solution of value for damping. Okay, I have one more problem, but I can take this problem later on. So, I will stop here today. Thank you.